A distinguishing trait of aerospace technology is its inevitable change. The Air Force has always been dedicated to the advancement of science and engineering. As a result, it is continually applying new technologies to the production of superior weapon systems and equipment. This commitment becomes increasingly important as weapon systems become more and more complicated. In the Air Force, technology deals with the tools and techniques for carrying out the plans of our national defense. The direction and development of this technology is the mission of the Air Force Systems Command. More than 50,000 employees, including an officer corps in which nearly 2/3 hold advanced degrees, are carrying out this mission for one purpose: to advance aerospace technology so they can acquire superior Air Force systems at the most effective cost. By its very nature, much of this work is directed toward the future. AFSC is now laying the foundation of the future Air Force. Today, the command is planning for some of the most sophisticated aircraft ever imagined. Concepts are now under study for the advanced tactical fighter. Planners must consider what the defense threat will be at the end of this century, and what technologies we can count on to be available. These same considerations are critical in the development of future airlift systems that will deliver vital logistic support in the event of war. Bomber programs must likewise account for tomorrow's missions, payloads, and the type of environment in which these aircraft will operate. Some future aircraft will likely operate both in and outside the Earth's atmosphere as transatmospheric vehicles. An aircraft which went through these types of studies well over 20 years ago is now emerging as our new strategic bomber. The B-1 will have a radar signature only a fraction of the B-52's. It will contain advanced avionics systems to provide increased penetration capabilities. Along with its intercontinental range, it will have tremendous weapons-carrying versatility, including the ability to carry cruise missiles, both internally and externally. This aircraft and its subsystems represent planned advanced technology that is now materializing to fulfill a specific Air Force mission. In the meantime, AFSC scientists and engineers, acting for the Defense Advanced Research Projects Agency, are studying other future design technologies, such as those in the X-29A. Its unique feature is the forward swept wing design. Among its potential advantages are lower drag, high maneuverability, flexibility in design, and reductions in size, weight, and construction costs. Because of the stress on forward swept wings, a bonded fiber composite is used to increase the strength of the wings without adding unacceptable weight penalties. In addition, the X-29 has variable camber devices to alter the wing shape for changing flight conditions. In another area of flight technology, the AFSC F-16, or Advanced Fighter Technology Integration Program, has recently completed a one-year flight validation of a sophisticated flight control system. A computer-controlled flight system, along with some new control surfaces, allow this modified F-16 to maneuver laterally, change altitude without pointing its nose, and perform other unconventional maneuvers. The command is developing another flight control technology in the Integrated Flight Fire Control Program, or AFSC. The goal of this research is to integrate the flight control and the fire control systems of an aircraft, so the pilot can make the necessary gross steering adjustments to align a target. Then the fire control system takes over the fine steering adjustments to direct the aircraft into a firing position. Although this technology is being demonstrated on the F-15, it is generic in nature and could be applied to any modern fighter. To evaluate the AFSC system, a series of flight tests was conducted. It was first flown against tow targets in live firing demonstrations. The system allowed the pilot to destroy the towed target. Then, the aircraft flew against various manned aircraft in a variety of difficult angles and maneuvers. Even at difficult angles, the AFSC system scored numerous simulated hits on the targets. In a final demonstration, the F-15 was pitted against a full-size radio-controlled drone for a live fire test. The drone was scheduled to fly a series of maneuvers, beginning with the most difficult aspect angles at about 4 Gs. The F-15 trailed 18,000 feet behind. The drone went into a 4G turn at 400 knots. The F-15 pilot also went into a turn, and when closer to the target, he coupled the AFSC system.
Keep the cameras going. Keep the cameras going. He's out of there. He's out of there. All the way. First class fireball out of there. Scratch one drone, RCA.
Of the rounds fired, the system scored an unheard of percentage of hits at that difficult an angle. This amazing success verified that the aircraft gun could be an all-aspect weapon and not merely used to hose down targets from behind. The command is continuing development of the Integrated Flight Fire Control System to adapt it to the air-to-ground gunnery and bombing modes. Future aircraft, whatever their configuration and advanced systems, will also be employing new materials for major structural parts. The command evaluates new materials as it continually seeks to improve the critical strength-to-weight ratio. One of the most promising developments is boron and graphite composites. Systems Command engineers have already demonstrated that this material can equal or better the performance of metals in primary structures, like wings, and that it can be repaired after sustaining minor battle-type damage. Research is continuing into the repair potential of this material after severe damage. Some Air Force aircraft already contain composite materials, but as new aircraft enter the inventory, they will be built with even more advanced composites. Just as the technologies of new materials are accelerating, so are the processes used to build materials and aerospace systems. A major thrust in this area is the Integrated Computer-Aided Manufacturing, or ICAM program. This effort is aimed at increasing the productivity of the aerospace industry in the United States. The command is advancing the state-of-the-art in basic aerospace manufacturing technology and methods to establish a uniform system in the aerospace community. A system that integrates various stages of manufacturing processes could benefit all major areas of contracting work. By managing efforts involving the latest in computer technology, AFSC is striving to develop an overall ICAM architecture that could be individually tailored to accomplish almost any manufacturing task. On the shop floor, this would manifest itself in computerized machinery and robotic systems that perform both routine and complicated tasks. These systems would produce cost-effective and quality items for future Air Force products. Work of this type is, at the same time, advancing computer and other electronic technology. Perhaps nowhere is this more evident than in the area of simulation, where Systems Command has been a major developer for several years.